Hello, in this video we're going to take a look at using recursion in 2 dimensions, and specifically the flood fill algorithm, which will make sense to us in a moment. But first, let me introduce the problem. You may not know this, but sometimes I like to spend my free time walking through the forest. So this here is a picture of a forest that I've walked through in the past. This is an overhead shot, so obviously I took out a helicopter and rented it and then snapped a few photos, and this is what it looked like. And so these green spots, these were trees in my forest, and the black spots were places where there weren't any trees. And sometimes when I'm out enjoying the forest, I like to think to myself, if I were to light this tree on fire, what other trees would burn down? So for example, if I lit this tree on fire, well, as you know, if the trees are contiguous, then they're going to set each other on fire, so all this region will catch fire. But this tree over here, since it's on a diagonal, it will be safe because it's not really touching here. And these trees over here will be safe. So if I were to set this tree on fire, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 trees would burn. And I did this for a while, but it turns out society frowns on walking through the forest and setting fire to trees just to see how many burn down. So we can do the next best thing. We can burn virtual trees. So here's some virtual trees, and I'm going to click on them to see how many burn. And to determine that, we're going to write a little method called burn. And so here's my burn method. And burn is going to be recursive. It turns out this is an excellent case for using recursion. Recursion is going to be easier than trying to solve this without recursion. So let's do that. If it's recursive, I'm going to have at least 2 cases, a base case and a recursive case. Remember, recursive methods are ones that call themselves, so I need a case where I don't call myself and a case where I do. That seems to involve an if. So what is my simplest case? What is my base case? Well, my base case, what's the simplest thing I could burn? Well, maybe this is the simplest thing I could burn because this tree is all by itself. But you know what's even simpler than burning one tree? Burning no trees, right? In fact, you're probably burning no trees right now. See how easy that was? So if we just click on one of these black squares, that's going to call my method, and it's going to realize that since the square is black, no trees should burn. So let me actually give you a little bit of background, and I don't want you to get caught up in the specific classes and objects and stuff that I'm using here. The real point here is to understand recursion, regardless of the specific Java classes that I'm working with. But just to give you a little bit of background, G is my grid, and that's where my trees and lack of trees are, and loc is the particular location that I have set fire to. And so the simplest thing might be if that particular location is not a tree. And the way we can do that is we can figure out if I get the color, I ask the grid for the color at that location, and if that does not, hence the exclamation point, if that does not equal the color green, then that will be my base case if it's not green. And in fact, I'm going to make a note that green is a color that is no part red, all green. That's 255. These numbers are from 0 to 255. I'm sure we'll see more of this color idea in another video. No red, all green, no blue. So that's the green. That's the green color, and if the color here is not green, that's my simplest case. What should I do in the simplest case? Well, do nothing. There's nothing to do. There's nothing to burn. Although I can't just do nothing because my method is supposed to return a number, and that's the number of trees that burned. So how many trees burned when I set fire to nothing? None. Alright, that brings us to the more interesting case, which is I actually get to burn some trees down. Alright. And I realize in order to keep this on one screen, I'm going to play some games here with my braces. So we'll just tuck that away. This one has only one line of code. So we'll just sort of squish that together. And if I've already returned, I don't really need an else, because I know I'll never get to this point unless the color is green. So at this point, I know that loc is green, that the color at loc is green. So what should I do? Well, I'm supposed to, I've step 1, I wrote if, step 2, I tested for my simplest case and handled it. Step 3, I'm supposed to write the recursive call. So the method is called burn, and I'm going to pass the same grid, but a different location. Which different location should I pass? Well, if I set fire here, it seems like I should make a recursive call, one above, but also below and to the right and to the left. I should make one recursive call for each of the 4 directions I can go. So there will be 4 recursive calls. In fact, this is really where recursion pays off. When I have multiple recursive calls. For problems with multiple recursive calls, recursion is great. Writing this same code without recursion is going to be a lot uglier. Well, not super ugly, but uglier. So I want to burn the tree that's just above me. And that would be, let's see, the same, let's see, I can ask a location for its row. So above me, let me tell you how my rows and columns work, just in case you don't remember or you haven't seen this before. This is row 0, row 1, 2, 3 going down the page, and this is column 0, 1, 2, 3 going from left to right. So to go up, I subtract 1 from the row, right? Go up, you go to a lower row number, and the same column. So this is 1 row up, same column. That gets me a new location, and now I can burn it. And I'm going to do that same thing. In fact, I'll just copy and paste 4 times. 1 row up. Let's see, if I go left, the cell to my left is the same row, but 1 lower of a column. The cell to my right is the same row, but 1 greater column. And the cell below me is the next row, row plus 1, and the same column. I realize that's probably off your screen, so we'll just slide it over there. Okay, and now that I've said that, I'm going to make it go off the screen, because what I'd like to do now is, I remember that when I make a recursive call, a great thing to do temporarily is to save the result. So this was the result of burning, I'll just say up, left, right, and down. And then I ask myself, if I have all those answers, how does it help me? If I know the number of trees that burned up, left, right, and down, how can I figure out the total number of trees? Well, the total number of trees would be up, plus left, plus right, plus down, right? Well, not exactly, but we're getting there. Let's see how it does. We're going to learn by trial and error here, which I think will help us. So, it turns out I've already programmed it, that when I say test burn, that pops up a forest. On forest, and when I click, it will actually call the burn code I wrote. So let's start simple. Let's click on a black cell, and it says no trees burned. But for some reason it's thinking. That has me nervous, but it says no trees burned. Let's click on another black cell. No trees burned. This is working. Okay, let's get daring. Let's try a green cell. Let's try this one all by itself, and it says no trees burned. Really? So when I click on a black cell, or sorry, on a green cell, it's saying no trees burned. Why is it saying 0? Ah, because when I try to burn the location above me, that will get me back 0 because the color isn't green, and I will get 0 back from the location to my left and 0 for the location to the right. So I'll have a 0 back from this one, this location, and this location. And when I add those 4 zeros together, I'll get 0. The problem is I didn't include the original tree that I burned. So I need to add all of those numbers plus 1 more to include the original tree. Let's try again. I'll compile it, and we'll run it. Here we go. And we'll try another. Let's make sure we didn't screw up the black ones. Yep, still 0. Let's try a green tree. And I click, and it says 1. Hey, we're in great shape here. Let's try another one. How about, what else looks reasonably simple? How about these 2 over here? Whoa. Did you see what happened when I clicked that? We see that burn called burn called burn called burn, and then we had a Stack Overflow error, our favorite error message when we're working with recursion. So apparently we have an infinite recursion, and eventually Java ran out of stack space to keep track of all those recursive calls. So line 72 is calling line 73, which is calling line 72, which is calling line 73. Let's take a look at line 72 and line 73. Here's 72, the one that burns by going left, and here's 73, the one that burns by going right. Now why would this one call this one this one? Ah, because when I try to burn this cell, I don't remember which cell it was, but maybe it was this one, then it will burn to the right of that, which will involve burning to the left of that, which will require burning to the right of that, and so on. We're never stopping. We never realize that we've already burned a cell. So, or burned a tree. So we need to make sure we keep track of which trees burned. So, in the next video, we will pick up with this and we'll make a note. Must keep track of which trees burned so that we don't try to burn them again. So we'll pick up there in the next video, and soon enough, I assure you, you'll get to see the forest burn down. Stay tuned.